Hello, here we're going to go through a question looking at some power. We've got a van of mass 1400 kilograms accelerating at a constant rate 0.2 meters per second squared, traveling up a slope inclined at some angle theta to the horizontal. It's got resistive forces in total of 4,000 newtons. When the van is traveling at a speed of 20 meters per second, the power output of the van's engine is 91.1 kilowatts. So we need to find theta. So first of all, let's use our skills at drawing force diagrams just so we can get everything marked on. So we know we've got a slope. There's our slope. We've got a van, which I'm just going to do as a block. The angle of the slope is theta. We know that the mass of the van is 1400 kilograms. So let's draw on our weight. So arrow straight down from the center of mass, 1400 G. We're going to have our normal reaction force going up there, some value R. So we've put that on, we've put that on. We've got a constant acceleration of 0.2 meters per second squared. Put that up the slope. What we got? Total resistance forces of 4,000 newtons. So if it's moving up the slope, the resistive forces are going to be down the slope. So we've got 4,000 going that way. It's given us this information. Is that going to be enough for our diagram? Well, clearly it isn't, although it hasn't specifically said it. It's obviously implied in the question that the van must have a driving force going up the slope. At the moment, we don't have any force going up the slope. There has to be something that's driving the van forwards. So let's mark on that arrow and we'll give it a D for driving force. Right, so that's drawn our picture. And we're also saying here when the van is traveling at 20 meters per second, it's got that power output. Right, okay, well, we can come back to that in a moment. Right, the first thing that we're going to need to do is apply Newton's second law. So we'll do our F equals ma because they've given us the acceleration and we've got a load of forces. So why wouldn't we do this? And we can do this parallel to the slope because that's going to get rid of one of our unknowns in R and it's the direction that we got our acceleration in. So let's resolve our forces. Going up the slope, we've got D. Going down the slope, so put in negatives on them, we've got our minus 4,000 for the resistive forces, and then we've got 1400 G sine theta. And that is going to be equal to our mass times the acceleration. So that is 1400 divided by 5, because acceleration is 0.2. Right, so we've got all of that. The other thing that we can use in this, because there's no point resolving perpendicular to the slope, because that's just going to tell us R, and R isn't helping us at all. I mean, there might be friction going on, but it's all combined into this 4,000 newtons resistive total resistance forces that we got going on. So R's no use to us. We need to use this power output of the van. So you think, well, power is the... So yeah, power, let's just remind ourselves of what is energy transferred per second. That's energy per second. So that is our force multiplied by our distance. That's our energy, that's our work done per second. In this case, distance per second is 20. So if we want to get force, which in our case is D, this is our driving force here, this F, now it is our capital D, then we need to divide the power by distance per second, which is the velocity. So that's just another way of saying that our power is force times velocity, something that you might remember. But that's just talking through it again so we can see where that all comes from. So we can say that D at that particular point, and therefore in general, because they haven't told us it's changing. In fact, we've got a constant acceleration, so it must be a constant driving force because none of the other forces are changing. So D is going to be our power, which is 91.1 kilowatts, divided by our velocity, which is 20. So we can cancel those zeros, divide that by 2, which is going to be 4,555 newtons. We can put that back into our equation 1. So let's put that into there, and then we've only got one unknown, and we can solve for theta. So we've got 4,555 minus 4,000, so we've got 555 minus 1400g sine theta, and that's got to be equal to a fifth of 1400, which is 280. So just rearranging all of this, we are going to get that sine theta is 555 minus 280, so 275, divided by 1400g. So we just need to do inverse sine of that, and it will give us what theta is. So tapping all of that into the calculator, we get theta is 1.147, so let's say 1.15 degrees. So yeah, nice question. They don't give an enormous amount of guidance, which is nice. I mean, you probably get more marks for this because they've broken it down into multiple steps. They've just told you to get on with it. But we're applying our same skills. We're doing our usual Newton's second law, but then we're adding in our new skills around power as well, just to sort of beef this up a little bit.